Okay. Let's see in that. Now I record my lectures. I record my lectures, but that lecture, third lecture. So sorry about that, but there's no recording of the second lecture. I mean, I do have the notes the scribbles that I make on my iPad as I do the lecture. I have those, and I could post those, but I think everything is covered in the notes, so I don't think I'll do that. Does anybody know how to set up a YouTube channel? If so, could you send me an email with instructions on how to do it? And
sure, yeah, I can send you an email. We've been doing it with another seminar, but it's a little bit complicated. Like, is it okay if it's like quite long?
Well, it is what it is, as Trump has been known to say. You know, send me what I need in order to set up the channel. And then, is there complications moving the Zoom file to YouTube? Or is
no, that part is fine.
That part is
yeah, fine.
It's just great. I now have a new thing that Dave Meyer was telling me about that it suddenly appeared that I didn't have before, which is a pointer, which I don't know how it works because it just appeared on my iPad. But I had at least one complaint from somebody last time, which I think was completely justified, that I was talking about, well, this piece here and that piece there, and nobody could see what pieces I was referring to. But there's some way to use a pointer, but I don't know how that, oh, I see. You can see the red dot, right?
Yeah, what's even better, go tap on the thing itself. Go tap on the control the same way you pick a color. Okay,
yeah.
Hold laser tail, turn that on.
All right. Okay.
Now play with it, and as long as you hold it down, it holds the line and it disappears on you.
I see, cool.
It's really awesome.
We'll try that. So, yeah, Dave, you know, when I was talking to you, when was it, last week, I had updated my Notability, and that thing just wasn't there.
Yeah,
and
confused.
Suddenly this morning, it's there.
Well, you told me it wasn't there, and I knew it was always there. And then when I went next to use it, it wasn't there for me too. It's like, oh my God, I caught it.
You caught the bug.
Yeah, and then I looked it up. It was just, it only works when you're hooked up.
Well, what do you mean it only works when you're hooked up?
It doesn't show unless you're sharing your session. Somehow they know
so
that
maybe
you're sharing it over
when I was talking
Zoom.
to you about it, I wasn't sharing.
Right. And then when I checked next, I was making notes up and I wasn't sharing. They should have it grayed out, but they didn't do that.
Okay. Well, anyway, if I start doing this sort of this piece here and that piece there, and you guys don't know what I'm talking about, somebody please stop me. And more generally, if you're lost, ask a question. I know there's a fair number of us still. I don't know how many. Looks like 20 or 30. But still, I haven't been interrupted by questions enough to perturb the lecture yet, since I've had no questions. So please, if you're lost, please feel free to ask a question. All right, so what I want to do today is make one correction from last time. What's in the notes is correct, but when I said it in, last Wednesday in the lecture, I got it wrong. Then I want to talk about the isotopy theorem, which is where I left off last time. And then moving, that'll lead us to moving the critical values around, up and down, past each other. And then we get to self-indexing Morse functions, which is what we usually use. I mean, they're just very convenient to work with. And that leads us to the Morse chain complex, Morse homology. And if I have time at the end, I'll talk about the Botten-Morse case. So that's my plan for today. I see I've started in the portrait mode, so let me move to landscape mode. All right. So the correction from last time had to do with moving the critical value within a canonical neighborhood. So my picture of a canonical neighborhood, remember this could be from Euclidean space. We have the value of the critical point. So here's the critical point. Critical value is C. And this neighborhood is going to be bounded below by, always do that, by F equals A, which is less than C, and bounded above by F equals B. So remember, the actual neighborhood sits over this picture. The generic fibers are products of an R sphere. R's is going to be the index of the critical point. An R-1 sphere across an N-R-1 sphere. Over the origin, you have only one point. Over the x-axis, you have the sphere from the y direction, the S N-R-1. And over the x-axis, you have the sphere for the x direction, the S R-1. Over the y-axis, you have the S N-R-1. The flow preserves the spherical coordinates in both directions, but of course it varies x and y. So flow lines look something like this, of course. So our canonical neighborhood is going to be bounded by flow lines on the outside, and then bounded below by F equals A, bounded above by F equals B. So this is the region we have in mind. Of course, back up in the pre-image. And if we think about what this looks like, okay, well, that's our canonical neighborhood. Let me actually draw this one dark. So that's the neighborhood, and we'll call it N, and it depends on, well, I guess it depends on the a size epsilon, which I'll talk about, the lower bound, which is F equals A, the value of the critical point, which is critical value C, and the upper bound, which is B. And here epsilon will be the norm of Y in the F equals A hyperplane submanifold. So it's, where'd it go? It's this distance here, measured in the Y coordinate. So I think of this as being small, but it's free to be any amount. So that's what it takes to define this neighborhood. The bottom level, the top level, the value of the critical point, which has to be in between, and the size here. If I'd wanted, I could have also taken the size up here, and they're related by some function depending on A, B, and C. But I won't work that function out, just what the flow lines of the hyperbolas look like. Okay, so that's a neighborhood. I have the critical point. I want to move the critical value up from C to some C prime. So now I have some C prime in the open interval AB, and I want to move f until f of the critical point is equal to c prime without changing any of the basic structure here. So the flow lines will be the same, and this will be canonical coordinates in a neighborhood of the critical point. Okay. So what I'm going to do is take inside this neighborhood a smaller neighborhood, which I'll call N naught, of the same general type. So it will go from A to B. It will still have, of course, a critical point at level C, but epsilon, say, is replaced by epsilon over 2. So it's a smaller neighborhood inside the bigger neighborhood. And I'm going to take a diffeomorphism from the interval AB to itself, which sends A to A, B to B, and is the identity near A and B. So the identity near the endpoints. And sends C to C prime. All right, so I have an interval, I'll draw it vertically, A, B. Here's C, our original critical point. I just want to move it up here, keeping the map, the identity near the two ends. Okay, so that's phi. And my function on N naught, so on N naught, I will use phi compose F. So all I've done is change the way I've parameterized the interval from A to B inside N naught. Okay. Oh, I also want phi to be a translation on some interval around C to C prime. So it just shifts up by whatever amount. So then these coordinates will be canonical coordinates in some smaller neighborhood, smaller than N naught. All right. So that's what I do in N naught. Now I have to damp that out so that I get the original function f out on the boundary and near the top and bottom. Okay, so so I've got a function here. It does agree on this little piece of top and bottom with what f originally has the same value as f, just because the map's the identity near A and B. I need to extend the map so that it's constant B here, constant A here, and damps out to F. And I want to do it in such a way that the gradient field here, or the gradient of the original function, is still a gradient-like vector field for this damped out version. So I'll take a function mu from the interval epsilon over 2 epsilon into 0, 1. So epsilon over 2 epsilon is, remember, what's parameterizing the levels between N naught and N. Okay. So this is going to be a function that's, say, identically 1. Mu is identically 1 near epsilon over 2, and mu is identically 0 near epsilon. And then I'll simply form mu times phi compose F plus 1 minus mu times F, whereby mu, I've defined mu as a function on this interval here, which is a radial coordinate in the y direction. I simply project this product onto this annulus in the y coordinate space, pull the function back. So I have a function that's constant on every flow line, and in fact only depends on the radial coordinate in the y direction. So mu is really, the function mu is really mu of pi, mu of y, of norm y of pi, where y is this is the y coordinate. So the y coordinate is telling us where we are along this disk. I'm only taking its norm, and the projection is a projection along the flow lines from this whole annular region between n and n naught, this annular region in here between n and n naught, down to this annular region in y space, and then I take the norm of that projection and take mu of that. So I'm damping this function out by partition of unity, well, not a partition of unity, but a bump function, which is constant on the flow lines. And so you see that on any flow line, you simply have a linear combination of two functions for which the flow line is a gradient like vector field. So the linear combination will have that property as well. So by this damping out, I get a function for which the original gradient flow line is a gradient-like vector field for the new function. It agrees with f out here on the edge, on the bottom, and on the top. Okay. So that's, and I've moved the critical value from C to C prime, where C prime is arbitrary in the interval between A and B. Okay. So that's my correction from what I did last time. Last time I said just add a constant to f and damp it out. Well, that works pretty well in this region, but it shifts the top and the bottom, so it doesn't agree with what you need near the top and the bottom. So you have to be a little more careful than what I said last time. But if you look in the notes that I wrote, this is the way I did it. All right, so that's the correction. Now let's go back to the isotopy theorem. So our picture for the isotopy theorem is we have a cobordism, a Morse function with a singular critical point, with a single critical point. And here's this descending manifold. Here's boundary minus W. This is W. And then I have an isotopy, phi t, of the sphere SR minus 1. Let's call this P, SR minus 1 of P, which is in boundary minus of W. This is just the boundary of the descending disk inside boundary minus W. And I have an isotopy of SR minus 1 of P into boundary minus W. So I have some way to move this inside boundary minus W. Okay. Well, of course, I had not only F, I had a gradient-like vector field with respect to which I defined the descending manifold. And then the claim is that there exists, well, now take a band between P, below P and above boundary W. Let's say it goes from A to B. Okay. Then there exists a vector field chi with the following property, chi prime. Chi prime is equal to chi off of F inverse AB. So the only place chi and chi prime differ is in this band between A and B. So up here, chi equals chi prime, and below A, that is near the boundary, chi equals chi prime. Okay? And chi is a gradient-like vector field. Chi prime is a gradient-like vector field for F. And lastly, the descending manifold with respect now to chi prime has boundary inside boundary minus W equal to the image at time 1 of the isotopy of the sphere. Okay, so this result says, in this simple picture of a single critical point in a band where you're going to vary the gradient-like vector field, you can achieve any isotopy in the bottom level of the lower sphere by simply changing the vector field, in fact, by an isotopy. But that's not so important. All right, so here's how we're going to do that. So first of all, let's display the isotopy, and let's display it top to bottom from B to A. So the isotopy, I should say, in this region AB, I have a product structure. So in F inverse AB, we have a product structure. It's given by the projection onto the interval direction is simply F, and the projection onto the bottom level, which is F inverse of A, is simply given by flowing along the flow lines of chi. So flow down along chi. So that's the product structure. We've talked about this before. Anytime you have a cobordism with no critical points, the Morse function with no critical points and the gradient-like vector field determine for you a product structure. And in this product structure, chi is some positive multiple rho times d by dt, t being the coordinate in the interval direction. Okay, so we have a product structure. And so now we have an isotopy from the descending sphere wherever it ends up at level B. The flow under chi would just be vertical of this sphere. But now we have an isotopy, which we can display as an isotopy in the product. So in other words, it's now a level preserving map phi hat from the sphere cross AB into F inverse A cross AB. At the top, which is B, phi hat is the original inclusion. And at A, phi hat is phi sub 1, the result of the isotopy, of the original isotopy that we're trying to achieve. All right, so that's an isotopy on this submanifold, the subsphere. We have the isotopy extension theorem that tells us there exists an ambient isotopy. H from M cross AB to M, or M cross AB. Let's do it in the displayed version. So that H restricted to M cross B is the identity, and H restricted to the sphere cross A is phi 1 of the sphere. So we have this isotopy of the submanifold. We extend it to an isotopy of all of M. So, and the track of the isotopy on the submanifold is simply the image under the ambient isotopy, which starts at the identity of the inclusion of the sphere. Okay. All right. And now we push for, well, I want to push forward the vector field by this isotopy, but I want it to match, at least the flow lines to match, with what I have coming in, which are vertical flow lines, and what I have going out, which are vertical flow lines. So to do that, you simply take what I call a weak reparameterization of this isotopy by taking some function psi from AB to AB, which sends A to A, B to B, is constant near A, constant near B, and on the pre-image of the interior of the interval, it's a diffeomorphism. Okay. So instead of just allowing this isotopy to start boldly moving forward, you keep it the identity for a while. You keep it the identity for a while, then you let it move out over the same track, but a little bit faster, and then keep it the identity toward the end. And then that isotopy will match with the identity above, and if you will, well, so then the image of the vector field. So what I'm going to do now, once I've reparameterized so that my isotopy starts at the identity and then moves off and then ends constantly at whatever the image map is, I'll take the vector field chi prime to be, how shall I say this, chi above B. So above this level where everything's the identity, I don't change the vector field. It will be H star of chi in the interval AB and F inverse AB. That's where things change. And chi prime will be vertical between boundary minus W, the region between boundary minus W up to F inverse of A. Okay. So it's the vector field it was up here. It's the push forward of that vector field by this ambient isotopy, and then it'll be vertical below. So if you think about what happens to the descending manifold, well, coming out of the critical point, we have the same descending manifold till we get to level B. Now we've pushed the vector field forward by this ambient isotopy. That will simply have the effect of pushing the, what used to be a vertical part of the, in the product structure, a vertical part of the descending disk will now follow the isotopy down to A, and then after that it will be vertical. Okay. So chi equals chi prime up here, chi equals H star of chi here, chi prime, and chi prime is vertical here. So this is a gradient-like vector field for the original function f, and it moves the bounding sphere in boundary minus W exactly to where I want, namely the image of the isotopy. The one property it doesn't have is that in this region below A, it doesn't agree with chi. It has the same flow lines as chi, vertical flow lines, but it won't have the same scaling. So below A, chi prime is some positive function times chi. Two vector fields with the same flow lines differ by scalar multiplication by a positive function. So we can simply damp this, we can take the inverse of this function, use and vary chi prime by that in this region, and then damp it out to 1 in here. And that won't change any flow lines. And so we just multiply chi prime by rho inverse below A, and then damp out back to chi prime in the AB region. So we have to change chi prime by some positive function in the region between boundary minus W and B. But that doesn't affect any of the flow lines, doesn't affect the descending manifold. And now, after we make this change, chi agrees with chi prime agrees with chi above B and below A. So that's the change in the vector field. So that's the proof of the isotopy theorem. Any questions about that argument before we go on?
Oh, I get a little bit lost in the original construction. Why does chi below B changed?
Why does chi?
Below A. I mean on the bottom part.
I should have said above. That's a typo. So sorry, the picture is correct. So chi and chi prime are going to agree up here above B. Chi prime is going to get changed below B by the isotopy in the region between A and B, and then it just becomes vertical again in B, but by a different scalar multiple.
Okay.
So I think I wrote below, but I meant above. That's all.
Oh yeah. Yeah, my question is about in the construction. Why does the part between A and partial minus W change?
Yeah, because we have this product structure where chi is a multiple of dt, but it's not equal to dt, and that multiple varies. So restrict to this region A here, and ask what chi looks like along A. Well, it looks like some function rho of W d by dt. So that's what the original vector field looks like here. So chi is not d by dt. Chi is just some positive multiple of d by dt. Because I want the function f to give me the levels here, to give me the projection to the interval. So I can evaluate chi on f. I won't always get 1. I'll get a positive number, but I won't always get 1. Chi does have vertical flow lines. That's how you define what vertical meant. But it's not moving with speed 1 with respect to the coordinate measured by f. So chi is simply a positive multiple of dt. Now you move this level set around by diffeomorphism. And so suppose the diffeomorphism takes W to W prime. The original vector field was rho of W d by dt here and rho of W prime d by dt here. But the new vector field at this point will be rho of W d by dt. So I will have transformed this function by the diffeomorphism. And since the function is not constant, I'll get a new function. Yeah. And you do the same thing all the way down. You just apply the constant diffeomorphism down here. Since the vector field looks like this, it will change to a vector field h star of rho d by dt. It's a different positive function. So you have to interpolate in between those two. That's all. Yeah. I mean, I could have set chi up to, I could have multiplied chi so that it was d by dt in this whole region to begin with, and then I wouldn't have had this problem. Okay. All right. Any other questions about that? No, that's a good question. All right. So now I want to use the isotopy theorem and the movement of critical points in a standard neighborhood to start moving critical points in a general cobordism around. So suppose we have two critical points, P and Q, and the index of P is R, the index of Q is S, and R is greater than or equal to S. And let's look at some intermediate level L, and suppose that no other critical point, there's no other critical point whose critical value lies in the interval under consideration, say from slightly below P to slightly above Q, A and B. These are the only two critical points with critical value in the interval AB. Here's an intermediate value L. So I have the descending sphere from Q down to level L, which is a sphere of dimension S minus 1. I have the ascending manifold from P, which up to this level, which is a sphere of dimension N minus R minus 1. L, of course, has dimension N minus 1, so codimension 1 submanifold. So the sum of the dimensions of these two spheres is N plus S minus R minus 2. So as long as S is less than or equal to R, this is less than N minus 1. So you would expect, as I said last time, generically these two spheres will be disjoint, but there's no reason to expect them to be disjoint. It could, unfortunately, non-generically, look just like that. But there's an arbitrarily small isotopy that moves either one of them. I guess since I was doing descending manifolds, I'll change the vector field. I'll change chi in this region to deform this sphere by a small isotopy. So I change chi slightly above level L to move the descending manifold SS minus 1 of Q off Sn minus R minus 1 of P. Okay, just by a small isotopy, I move this so it misses, okay? Just by general position. All right, well, at this point, the ascending manifold for P extends up all the way to level B, because the ascending manifold from P does not meet the descending manifold from Q, and there are no other critical points in this region. Therefore, the flow on this sphere at level L passes the critical point and goes all the way up to level B. Okay. And of course, the descending manifold from P goes down to level A. So I have, sorry about that. I have then this much of the standard picture embedded, standard picture from Euclidean space embedded. So here's, let's say, P, F of P is C. The lower level goes down to F equals A, and the upper level goes up to F equals B. Okay, so I have these, the pre-image of these two axes. The vertical axis is the ascending manifold that goes all the way up to level B, and the horizontal is the descending manifold that goes all the way down to level A. This should be. Okay, yeah, A and B. Well, if that's true for the ascending and descending manifold, it's true for any flow line that starts sufficiently close to the descending manifold. So if I take a small epsilon interval here and flow from that epsilon interval take the flow lines, they also will avoid the critical point, Q, and go all the way up to level B. So what I have then is an embedding. So I actually have an embedding of some standard region down to A, up to B, and parameterized by some small epsilon into M. So that this standard function F naught agrees with F under this embedding. In other words, F restricted to the image pull back is F naught. And chi pulls back to some positive multiple of the gradient of F naught. The positive multiple being 1 near the critical point by the definition of chi. And well, chi and this function by construction have the same flow lines, so they differ by a positive multiple. Okay. Now, so that's, I have this standard model embedded in the manifold. And now I know how to push this, the critical point up. I have some F naught prime of P is equal C prime, and F naught prime equals F naught near the boundary, the 3 parts of boundary, the bottom, the top, and this side. Okay. So I can replace the function F by a function that's equal to F outside this neighborhood and equal to F naught, well, the transpose of F naught prime by this embedding in the neighborhood. So this has the effect, so gluing F naught prime in gives us a new Morse function, which is changed only in this neighborhood, and F of P is now equal to C prime, which I choose to be greater than the critical point of Q. And I make no other change anywhere in the manifold. So no other change outside of AB. So this is a basic construction that allows me to move critical points past each other. So the upshot is we can move, when P and Q are adjacent critical points, we can move F of P above the value, the critical value of P above the critical value at Q if the index of P is greater than or equal to the index of Q. So I start with a Morse function where the critical points are distinct. I look for an adjacent pair for which the index of the lower one of lower critical value is greater than the index of the higher critical value, and then I reverse them. So doing that allows me to arrange that F weakly orders the critical points, in the sense that if F of P, if the critical value at P is less than the critical value at Q, that implies the index of P is less than or equal to the index at Q. So the picture of the manifold, here's the bottom, W minus, here's the top, W plus. Here are all the critical points of index 0. Here are all the critical points of index 1. Then you hit 2, and so on. Okay. So there, you might call this a weakly, well, it's an ordered Morse function, ordering the critical points by weakly by index. But now I want to arrange that all the critical points of a given index have the same critical value. Well, so I apply the same argument. Now move all critical points of index I to have same value, critical value, Ci. So to do that, say I is 1, we'll work in this region, the region here that contains all the critical points of index 1 and no other critical points. Well, I can pick some intermediate value there, and since the critical points all have the same index, I'm free to apply the previous argument and move the values up and down independently using the isotopy theorem and arrange that all the critical points, in fact, end up at the same intermediate value, Ci. Okay. Now I have to worry about the boundary. I want F restricted to the boundary, which is locally constant, to actually be constant at some number C minus 1, which is less than C0, and I want F at the upper boundary to be constant Cn plus 1 greater than Cn. Well, I can do this because I have collar neighborhoods of boundary plus and boundary minus, where F is increasing as I go away from boundary minus and increasing as I come toward boundary plus. I can just stretch those out. The plus one I can stretch up as far as I want. The bottom one I can stretch down as far as I want. So I can arrange this. So now I have a function. Now I simply take psi mapping the interval C minus 1, C minus 1 to Cn plus 1 to the interval minus 1 to n plus 1. That's what happens to the endpoints, so that Ci goes to I. Diffeomorphism that does that. Right? And then F followed by psi is a map of W into minus 1 n plus 1, which is self-indexing. So that's how you construct self-indexing Morse functions. Any questions about that argument? So all that argument used was the isotopy result and a general position result that tells you that you can move submanifolds whose dimensions don't add up to the ambient dimension by an arbitrarily small isotopy until they're disjoint. Okay? Now, self-indexing Morse functions are very nice. One nice consequence of having a self-indexing Morse function is you have a very nice description of the Morse chain complex, which is what I want to talk about next. This is an analog in smooth topology or Morse topology of the CW complex, CW chains on a CW complex. And in fact, one can construct a homotopy equivalence from a manifold with a Morse function to a CW complex that has one cell for each critical point. The dimension of the cell is the index of the critical point, and they're attached in the same order. But I won't go through that. Rather obvious construction. Anyway, so we have a self-indexing Morse function on an N manifold. And I have a gradient-like vector field. Let's define WK to be a compact submanifold that contains all the critical points of index K. So we'll go from K minus a half to K plus a half. So K minus a half is a regular value. K plus a half is a regular value. And all the critical points of index K lie here right in the middle. Okay. Let's consider the homology of WK modulo its negative boundary, which is the preimage of K minus a half. Okay. Well, I claim that this homology is 0 except in dimension k, and it's free abelian for star equal k, and I'm even going to tell you what it is explicitly in star equals k. The point is that, as I showed you last time, well, I showed it for a single handle, but the same argument works for multiple handles all at the same level. There's a deformation retraction of WK onto boundary minus WK union over the critical points of the descending disks for the critical points. So here's our Bordism. Let me just draw 3 critical points. P1, P2, P3. We have these descending disks, D of P1, D of P2, D of P3, and they're all disks, these are K disks, because these are the descending manifolds for critical points of index K. So you have a deformation retraction, which away from the ascending manifolds is simply the flow, and then near the ascending manifolds you use the local picture to have a deformation. You have the deformation coming from outside, which just flows along these lines. You have to extend that to a deformation of this picture like that onto the bottom and the disk, the descending disk. Okay, so you do that near each critical point. I talked about that last time, 2 times ago. All right, so we see now that the homology of WK modulo its negative boundary is simply the direct sum over the critical points of the homology of dk mod its boundary. So it's certainly concentrated in degree k, and it's free abelian in degree k, and a basis, an ordered basis, is determined by ordering the critical points, or numbering them if you want, and choosing an orientation for the descending manifold out of each critical point. Once you choose an orientation for the disk, that gives you a fundamental class for the disk mod its boundary. You reverse the orientation, you get the opposite fundamental class, and those classes give you a basis for the homology of this relative homology. Okay. So this is the definition of the kth chain group for the manifold with respect to the Morse function and the gradient vector field. Doesn't really depend on the gradient vector field in some sense, though the boundary map will, because the basis for this is a free abelian group in degree k, and its basis is given by the critical point together with an ordering for the negative negative definite subspace of the Hessian at the critical point, which is the tangent space to the descending disk. So you can say it without using chi. But anyway, I'll put the chi in. So it's HK of WK boundary minus WK. Well, to have a chain complex, I need a boundary map from CK. I'll drop the extra information. So CK is this thing, okay? So I have to define a boundary map. Well, mirroring what we do in CW homology, let's define it this way. We go from HK of WK, comma, boundary minus WK, into HK minus 1 of boundary minus WK. This is the usual boundary map. But this is HK minus 1 of boundary plus WK minus 1, because boundary plus of WK minus 1 is equal to boundary minus of WK. And then I go by the inclusion into HK minus 1 of WK minus 1, and then by the relative long exact sequence to the relative homology on its negative boundary. It's completely clear from this description that boundary squared is 0, because I took a relative class, I took its boundary, I thought about it as a cycle in WK, and then WK, why is this? Yeah, so that's boundary. These cycles don't have, by the time you get here, there is no boundary. So when you take the boundary again, you would be going down to HK minus 2 of boundary minus WK minus 1. That would be the first step in the next boundary. But this composition is 0. So boundary squared is 0. It's the usual argument. Okay, so this is our chain complex. C star depends on, well, now it turns out it does depend on chi, as I want to show you. So I want to get a different description. So this is a purely homological description, if you will. I want to give a more geometric description of the boundary map. Okay. So this is all going to take place at this intermediate level, boundary minus WK, which is boundary plus WK minus 1, which is the level set F inverse of K minus a half. So I have these critical points of index K up here. Let's say they're Q1 to QK minus 1 to QK. And I have the critical points down here, P1 up to PL. I have the descending manifolds coming out of the critical points. Let me have a fewer, not quite so many critical points. I have the descending manifolds coming out of the critical points Q, and I have the ascending manifolds coming from the critical points of P. This time, if you do the boundary computations, you will find that the sums of the dimensions of these spheres is exactly the dimension of the ambient manifold n minus 1. So let's just do that real quick. So these are points of critical points of index K, index, and these are critical points index K minus 1. So the descending manifolds from the Qs at this intermediate level are spheres of dimension K minus 1. And the ascending manifolds from the Ps are spheres of dimension n minus K, because P is a critical point of K minus 1, so codimension is K minus 1, dimension is n minus K. And these generically meet in points, transversely in points. So my picture is misleading because I don't have quite enough room to draw it. because in this picture, it's a one manifold and these boundaries are zero manifolds and they look generically disjoint. But in fact, in real life, the dimension of these spheres is complementary, so you expect the collection of spheres to meet, well, generically at least, transversely in points. And again, using the isotopy, I can arrange this generic intersection. Okay, so the descending spheres from QI, a descending sphere from QI intersects an ascending sphere from PJ in a finite set of points. Each is transverse. That's my generic assumption. So I've deformed the vector field a little bit by an isotopy until I've arranged that. Now let's think about orientations. I haven't assumed that anything is orientable. Of course, these disks are orientable, and I have chosen orientations of the disks. So the descending manifold from Q, so the SK minus 1 from Q is oriented because it's the boundary of the disks from QI, which has been oriented. I chose that orientation. That will determine an orientation of the descending sphere. Okay. Now, the ascending manifold, I have not oriented. What it is what you might call normally oriented. So it doesn't have an orientation which would relate to its tangent bundle. I mean, it is orientable, but I haven't chosen an orientation. But what I have chosen is an orientation for the descending manifolds from the critical points of index K-1, the P's. And if you remember the local picture, the descending manifold and the ascending manifolds meet transversally. So this is descending and this is ascending. So if I orient the descending manifold using the fact that the ascending manifold is contractible or connected or simply connected, I guess, well, connected, that gives me an orientation for the normal bundle of the ascending manifold. It's normally oriented by the choice of orientation of the descending K-1 manifold from PJ. Okay. So now let's look in our level here, this K-1/2 level. I have these two spheres, here they are. This one is oriented, and this one is normally oriented. So it makes sense to compare the orientation of the first one with the normal orientation of the second one. They either agree or different, because they're crossing transversely, the orientation of this thing, of the second sphere, is a normal orientation of the first sphere, is a normal orientation to the second sphere, but the second sphere has its own normal orientation, so you get a sign of intersection. That depends on your choice of orienting the two descending manifolds. Okay? I don't need an orientation for the ambient manifold to do this. So then our S, what was it, K-1 of QI intersect Sn-K of PJ has a sum of plus and minus 1. Well, I don't want to say this. Just as a set of points, it was x1 to xt, but now each xi has a sign determined by these orientations, plus or minus 1. And so we can form the sum over I of the signs. And that's, of course, the algebraic intersection. Call it alpha I j. And the boundary map of qi, or of the, well, I should say, the boundary map of the basis element that goes with qi in the orientation, which is the dk qi mod its boundary, is a summation over j of alpha I j of the dk minus 1 pj mod boundary. So this will look familiar from the Floer homology, for example, in the infinite dimensions. This is the finite dimensional version, which of course came first. So these intersection numbers are the boundary map. Once you deform the vector field to be transverse, vector field so that the intersections are transverse, you can read off the boundary map from the algebraic intersection numbers of the descending spheres with the ascending spheres. So that gives you a geometric description of the Morse complex. And of course, an easy inductive argument shows you that the homology of the Morse complex is equal to the usual singular or topological homology of W mod the boundary. Just an excision argument working up one chunk at a time. Well, it's a completely standard argument. I don't think I'll go through that. All right, so that's the Morse chain complex. That's its definition, purely homological definition. Its more geometric definition in terms of intersections of ascending and descending manifolds, and then the basic theorem about Morse homology, that this chain complex calculates the homology of the manifold mod, its boundary and negative boundary. All right. So I have 10 more minutes. So I have a choice now. I could spend 10 minutes talking about the Bott-Morse case, just as an aside, which will come up and be important when we get to Bott periodicity, or I could start the introduction to the H-cobordism theorem. I'll take a vote. First 3 people who speak up get to choose.
Sketch the Bott-Morse.
There's 1 for Bott-Morse. Well, I sort of feel like doing that too, so I'll be number 2. There's the majority. So remember, a Bott-Morse function is not a Morse function. It's a map from, well, let me do the closed case, the real numbers. Has the property that the critical values are a smoothly embedded submanifold. And different components can have different dimensions. Okay, that's allowed. Secondly, the null space of the Hessian at any critical point so this is the maximal subspace on which the Hessian is identically 0, in null space. And of course, that null space is perpendicular to, under the quadratic form to every vector in the tangent space. Okay, so null space is equal to the tangent at P to the critical manifold. So Cm is the manifold of critical points. It's not hard to see that the null space of the Hessian has to include the tangent space of the critical points, even in the more singular world. If the singular points if the critical points formed a singular subspace, you would take the Zariski tangent space, and that the null space will include the Zariski tangent space. So in this case, the Zariski tangent space is just the usual tangent space since this thing is smooth, and the null space always includes that. But the second condition in Bott-Morse is that the null space is exactly equal to that. So if you look at along a submanifold of critical points, what you have is, well, in this space, in this direction, the function is constant, but in the normal direction, so normal to the critical manifold, f is a Morse function. It has an in the normal direction to this manifold, restricted to a normal space to the manifold. It has an isolated critical point. That critical point is non-degenerate, and so you see ascending and descending manifolds perpendicular to the critical point, perpendicular to the critical submanifold at every point of the critical submanifold. These, in fact, fit together to make descending vector bundles and ascending vector bundles. So we have what replaces the descending disk is a descending bundle E minus over the critical manifold, and the rank of E minus at a point P is simply the index of P. The index is constant, is locally constant, so it's constant on components. This thing becomes a vector bundle over the critical manifold. We also have the ascending vector bundle, which is dimension, the rank is the index of, index, I shouldn't say a P. Well, maybe I should. Index of F at P. So this is the index at P of minus F, number of positive eigenvalues. So the number of zero eigenvalues form the tangent bundle to the critical submanifold, and we have these two complementary bundles, an ascending bundle and a descending bundle. So that's the Bott-Morse picture. If you had a connected critical set, and you want, so suppose you have a cobordism with a connected critical set, a Bott-Morse function connected, then the homotopy type of W, so W will then deformation and retract to boundary minus W, union along the boundary of the descending manifold, descending bundle of the descending bundle. So that's the general statement. So instead of attaching a disk, you've attached a family of disks to boundary minus, parameterized by the critical submanifold. Those disks are all of constant value, the index of the critical point, which doesn't vary. And together they form a vector bundle, or a disk bundle inside a vector bundle over the critical submanifold. And that's what you've attached. And so the change in the topology of W compared to W minus then is the homology of the critical manifold, well, sorry, the homology of E minus, comma, boundary E minus, which by the Thom isomorphism theorem is the homology of the critical submanifold shifted up when you go from the critical manifold to the bundle mod the boundary by the dimension, by the index of the critical point. So you can do the same sort of thing we were doing for isolated critical points. You can separate the critical values according to their, well, you can separate the critical values so that the submanifolds lie on different levels, and then you can take chunks of the Bordism around those levels and get some sort of complex whose individual terms are these homologies of the critical manifold shifted by the dimension of the index, by the index in this way. And those all fit together somehow to make the homology of the full manifold modulo its negative boundary. It's no longer a chain complex. It's more complicated than that. What you're getting is a spectral sequence, and the individual pieces are the E2 term of a spectral sequence that converges to the relative homology of W mod the boundary. It just so happens that in the Morse case, since the individual pieces have homology concentrated in only one dimension, and those dimensions go up as you move up, the spectral sequence completely collapses and just becomes a boundary map of a chain complex. But in general, you'll get a spectral sequence to compute the relative homology where the E2 term is in terms of the homology of the critical manifold shifted by the index. So that's the Bott-Morse picture. Now, of course, you can get from the Bott-Morse picture to an ordinary Morse function. If you took a G just on the critical manifold, let's do the case of a connected critical manifold. So take a Morse function on the critical manifold and add to F some small multiple of the Morse function G. What that will do is it will tip this critical manifold slightly. You get a Morse function on it, and so you see finitely many critical points computing the homology of this manifold, and the critical points of this thing will be the index of F, which is what we recorded here, plus the index of G at the various critical points of G. So the critical points of this sum will be the critical points of G along the submanifold, and the index will be the index of G at that critical point, plus the index of F along the whole critical manifold. So you can split this homology into a little chain complex by just taking a slight multiple of a Morse function on the critical manifold. And of course, you recover the same homology in the end. So that's a way to get from Bott-Morse functions to ordinary Morse functions if you're so inclined. But often when you have symmetry, it's nicer to work in a symmetric picture where there's a group acting and let your critical manifolds be invariant into the group, so orbits of the group, and usually not zero-dimensional, not isolated. So that's the Bott-Morse picture. All right, I think I will stop here unless there are any questions. So you have a chance to ask a few questions. I will try to sort out the Zoom YouTube channel before Wednesday, and if and when I do, I'll let you know. Questions about today's lecture?
I have a question. It's not about today's lecture now.
Sorry, say again?
I have a question. It's not about today's lecture though.
Okay, ask it.
What is the picture near an isolated degenerate point?
I'm sorry, I didn't understand. What is the
picture near an isolated critical point that is degenerate?
what is the picture near an isolated point that's degenerate?
Yeah.
Well, we're going to we are going to have to consider, I mean, it depends on the critical point. There are many different models, and there's a whole theory of them, isolated singularities of hypersurfaces. Milner wrote a whole book on it. We will only need to consider the simplest degenerate points, and we've already seen them actually. Yeah, we've already seen them, the bursts. So here's a simplest degenerate critical point. I'll do it in t is a single variable, x and y are multivariables, and the function will be norm minus norm x squared plus norm y squared. So the usual non-degenerate Hessian in the x and y direction plus t cubed. Okay. So the only critical point is the origin. I'm sort of clear. The only place where all derivatives vanish. Well, here x and y only give you the origin. T cubed is critical. And 3t squared vanishes only at the origin. So the origin is the only critical point, but it's a degenerate critical point. So if you draw, let me forget x and y and just draw the function in the t direction, you see it's not transverse to the x-axis. Whereas, what am I trying to say?
Can I still associate an index to it?
No, well, does it have an index? Yes, because the Hessian, I'm sorry, so I misunderstood your question. So the Hessian of f at this critical point P, and it doesn't have to be isolated, always has a null space, a positive space, and a negative space. So in Bott-Morse, I was talking about the nullity. So this is the nullity, the null space being tangent to the critical manifold. Here you have a critical, this picture is not Bott-Morse. You have a critical submanifold, it's a single point, but the nullity is one-dimensional. In this case, the nullity is t, because the Hessian is minus 2x, 2y at the critical point in 0. So the null space here is given by the t direction. The plus space is the y direction, and the minus space is the x direction. Well, this is something you can do at any critical point, whether or not it's isolated. And the index is defined to be the dimension of this space, the number of negative, strictly negative eigenvalues. The nullity would be the dimension of the null space, and this would be the index of the negative. So this is, the dimension of this is the index. The dimension of n is the nullity, and the dimension of H plus is the index of minus f. So you always have that decomposition just by taking the quadratic form given the symmetric matrix of second partials of f at the critical point. So the quadratic form, the Hessian. But what the critical point is actually going to contribute depends on the higher order information about the function. So see, if you perturb this function slightly, and we've done this, you get so-called birth. So if you perturb this function slightly, you'll get minus, I'm forgetting x and y here, and nothing's happening there. If I perturb by t minus t cubed minus t, then I have two critical points, one of index 1 and the other of index this is index plus 1, index 0. The critical point of index 0 and a critical point of index 1. So this isolated singularity when you make it generic, breaks into 2 critical points of complementary index. More complicated singularities can break into any number of critical points. It's called the Milnor number. And then you can try to understand the indices of those critical points and so on. The index of every critical point will be somewhere between the dimension of the null space of the singular one, the null space of the singular one plus the negative space. Because what happens is, as you deform this quadratic form by a small perturbation, all the negative eigenvalues, they may shift, but they'll stay negative. All the positive eigenvalues may shift, but they'll stay positive. And the null space will get dispersed between positive and negative. And at different critical points, it can get dispersed, as we see here, in different directions. So when you perturb this to be generic, every critical point will have an index that lies between the index of the singular Hessian and the sum of the index of the singular Hessian and the nullity.
If you have a Morse-Bott critical submanifold,
Yeah.
can you perturb it so that you have one degenerate? So you can perturb it so that you have non-degenerate critical point, but can you perturb it so that you have one degenerate critical point?
I don't know right offhand. I doubt it.
Okay, maybe I can give you some context.
Okay.
So if you look at the homology of the loop space of S2,
Mm-hmm.
then let's say you give S2 the round metric, and you
Yeah.
do Morse theory with the energy functional where you have just the length function.
Yeah. The length, not the energy.
Yeah, well, okay. I mean, yeah. Let's say square root of the length or something. But then the critical submanifolds are Morse-Bott.
Right.
And I wonder if you can go from one of those critical submanifolds to one degenerate, maybe by perturbing the metric to
Yeah.
one degenerate critical point. I mean, one degenerate geodesic.
Yeah, well, I think that's an interesting question. Well, you're probably looking at not geodesics, but paths from one point, in fact, to a conjugate point. That's typically what you do. And then you get a submanifold, which in fact will be a circle in this case, of minimal geodesics. Well, I'm not sure. Let me think about that.
Okay, thank
I
you.
mean, are you really interested only in closed geodesics, or were you working in the path space?
No, I'm interested in closed geodesics.
Okay. All right. Well, let me think about it.
Thank
My
you.
guess is you can't do that, but I'm not sure right offhand.
I mean, the reason it seems like it could be done is that just the local product structure near. So if you do like if you do the product, then it seems to be the same if you have like a degenerate point, like maybe like a maximally degenerate point,
Uh-huh.
but critical submanifold. But I don't know how to go between the two.
Yeah. Well, let me see if I have anything to say about it. I'll have to think about that.
Thank you.
Sure. Anything else? Well, we've run over today, so I think it's time to quit. See you Wednesday.
Thank you.
Thanks.
Thank you.